Hello everyone, welcome back to our YouTube channel Becoming a ROS Developer. I'm Desire, and today I've got Francois, who has just completed the course Python 3 for Robotics, and he'll be giving us a presentation on that. So without further ado, let me hand over the platform to him so that he can begin his presentation. Alright Francois, whenever you're ready.
Yeah. All right. Hello everyone. Can you hear me?
Yes, I can hear you.
All right, pretty good. Hello everyone. Sir, I'm Francois Gonothi Toure, capstone project of the Python 3 for Robotics course that I took at the Construct Robotics Institute. So basically, I'm going to start off by showing how it works in the simulation and also in the real robot. And after that, we will talk about the structure and the strategy that we actually used in both code, in procedure-oriented programming, and also in object-oriented programming to solve the project. Yeah, okay. So basically, so like what we have here is like we are trying to implement two, let me call it like two strategies that allows us to move the robot in the smart city. So we're going to do it in simulation, and we have two ways in the Python for Robotics course. The first one is using the procedure-oriented programming approach, which is just based on you defining methods without choosing like classes or objects. And then the second one is going to be with like classes or objects, which is actually called object-oriented programming, or like using the object-oriented approach.
Yes.
So basically, I'm going to start off with is first of all trying to set up the simulation at first. That one is going to be pretty quick, and then I will come over here and then just try to source it, and I'll try to launch the gazebo simulator and also the ROS visualization simulator, so we can see like the robot in both simulations before launching the code. So as we can see here, we just have to wait for a few seconds, and we can see like the gazebo simulation actually or simulator actually sort of coming up. And then here just have to wait for a couple more seconds. The RVC is going to come up too. And what we are working with is actually in this Python basics project directory. So I'm going to try moving into that one, which is into, I think, the ROS workspace, SRC, and I think Python and Python again. So the codes are in here, and I'm going to try to launch the first one, which is like the procedure-oriented programming approach, which is like this one, the robot control, no class, so no object.py. So I'm going to run the Python script by doing Python 3. That's normally how we actually run Python scripts. And then writing the name of the file, which is like robot control no class.py, and then we just have to wait for it. And we see that it sort of just initializes and waits for like 5 seconds, and then it will start like running all the tests, like stopping the robot at first and then trying to run all of these, which are things that I'm going to explain a little bit later in the code. And it will start moving the robot, as we can see here. So I'm just going to maximize this a bit, and we see the robot moving here in our RV simulator, and then we see like it keeps moving forward when the clearance is actually okay. But like when it sees an obstacle, it stops first and tries now to decide, okay, what's the best direction that it has to take, and it turns towards that direction. So basically this is how it's going to work in the simulator. And I'm just going to, to minimize this window. So we have the two windows, like gazebo and RVs. And I'm going to stop this code and do also the same thing with the object-oriented programming approach. So basically going to be, I'm going to launch the simulator again by doing this. And this time I'm going to work with this code, which is robot underscore control underscore class.py. And then yeah, so it's gonna be the same thing. So it's going to be Python 3, robot control classed this time. So this one is using like objects or like classes, Python classes or Python object, which is like OOP. So when I run this code, we will see that the robot still behaves the same as it were doing when we did it with the POP, the procedure oriented programming approach. So we see here, I'm just going to maximize this a bit, and we see the robot moving, and then here it has seen like an obstacle, and it's going to decide, okay, what's the best direction to take, and it will take that one, and so on and so forth. So this is it, like on I mean, like how it actually works in simulation mode. So I'm going to stop that one, and now try to have it work in like on the real robot. So I'm going to do this and turn it on. We just have to wait for a few seconds to access the remote real robot lab that is based in, I think, in Barcelona, Spain. So now here we have we actually have access to the real robot itself in here, and I'm just going to bring it over here and try to maximize it a bit like this, and then I'll just try to use a web shell. This time we don't have to launch the simulator because we are accessing the real robot of this small smart city lab that is at the Robotics Institute itself. So basically I'm going to move into, I will just try to cd into the directory in which we have our code files. So okay, we're going to start with the first one. So it's going to be like robot control no class to test the POP. So I'm going to do the same command again, Python 3 to execute the Python script that we have, and then I'll call robot control no class to test that one out. So I will just boom execute it. We just have to wait for a few seconds, and it's checking, and yeah, it's going to start deciding, okay, where it has to go. So it has detected an obstacle over here, as we can see, and then it checks for the best clearance, and it's going to decide, okay, which direction it's going to take. So yeah, we see it going, and there also it has detected like the wall obstacle over here, so it's checking for clearance and deciding what's the best direction that it's going to take. So yeah, that's it for the procedure oriented programming approach for it to work in here. So I'm just going to maximize it a bit like this. Yeah.
Yeah.
Okay.
All right. So let's wait for it to complete the loop, and then we can move on to the class version.
Yeah. Sure. Yeah, I think it started over here. So we just have to wait for it to come back over here. Yeah. So it keeps moving. It sees the wall. I think like at a threshold of 0.4, like 300. Sorry, 400. I mean. And then yeah, if it sees, it checks for clearance and it decides what's the best direction. So yeah, it will keep just moving like that without bumping into any obstacle, whether it's the wall or like maybe let's say a traffic sign and so on and so forth.
All right. So let's see the class version and see if it performs equally as well.
All right, I'm going to stop this one here, and okay, we have the. Sorry. What's going on? Okay, so we have, I'm going to do this, Python 3 again, robot control, the classed version now. Then let's see what it's going to do. So first of all, it starts here and it's checking again. And yeah, now it just bumped into that one. Okay, it was struggling a bit to check for the best direction to take, and now yeah, it's avoiding it, because like what was happening at first, it's because it was really close to this, let me call it like a traffic sign, and it sort of just bumped into it and then decided where it has to move autonomously. So we have to wait again for it to complete like a full lap, like a full tour maybe, and yeah, it's going to perform the same way.
All right. Okay. I think this is good enough. So let's get into the code, right? That's where this whole detail is happening. So take us through what you did and the logic behind that.
Yeah, all right. Okay. So I'm just going to minimize this a bit and leave it moving like this.
I think you can terminate that so that it's not running in the background.
As I still have access to it, it's not okay. Sir, is this good? I think yeah.
Yeah, it is.
So
visible,
let's start
yes.
off. Yeah, absolutely. Yeah. So let's start off with the robot control node class. So as I said at first, like in this capstone project, we were actually asked to implement two possible solutions, or like, let me call it like two solutions to the problem we were like given.
Yes.
So basically the first is using procedure-oriented program, which is like POP, in which you don't use any Python classes or Python objects, right? So we start off the code by just importing like the Python like libraries that we need, and then importing also like the ROS libraries that we need, and yeah, importing this ROS robot interface that were actually given to us, and then we didn't have to change anything like in it. We import that one, and then what it does at first is that it checks, like it sort of like checks for movement and like sensor primitives. So at first it will define a method here that is called like stop the robot, and then like what it does is just like stopping all motion of the robot, and it sets the linear and angular velocity to 0, 0. And then it also defines another method which is called like move front, with an attribute like speed, and then this one drives the robot straight forward, as we can see, as we've been seeing like in the simulation and also in the real robots.
Yes.
And yeah, it's the same thing, and this other method here also does the same thing, like defining like a method turning left, turning right. So what happens here is that like when it's moving front, the angular velocity is set to 0, because like it only follows like a certain axis, so it's not like turning, it's not making any let me say like circular movement, right? So it sets this one to 0, and then the speed is just going to be defined for linear velocity. But like when it has to make a turn, it means it's making some sort of like circular movement. In that case, we set like the linear velocity to 0, and then we give the speed to like angular velocity. So that's how it works. Now it's making here a turn. Linear, it's like 0, and then the speed, like this one is gonna be negative, because like it's making like a right turn. And then here, like there is another method which is like defining a timed moved front. And in this one, what it does is that, okay, it tells the robot to move, go to a certain distance at a certain amount of time. So it's actually timed. So you tell it, okay, move for 2 seconds, move for 3 seconds, move for like so on and so forth seconds. Yeah, these are all timed like movements. So timed moving front, moving, turning left, turning right, and then these ones. And then it can also move like towards the front at a certain distance. Like this one is based on time, and this one is based on like on distance. And it's actually the same thing that we actually have here. And it also can actually do some sort of like turning angles. So like it can actually like turn angle left and then turn angle right too. So we start off by doing this first, and then after that we try to get like sensor data, because like it has like a sensor, yeah. So we try to get the sensor data. So basically we try to return the minimum range measured within like center angle and so on and so forth. Like yeah, here the angles are actually sort of measured in regions, and so the angles are measured with like the library that we imported at first, robot interface, and then scan ranges. And then we have the a min, that's like the minimum angle, and the increment, like the angle increment that we have here. And then we here n is going to be equal to the length of the angle, so like length of angles. And then we will do some sort of computations over here. So first of all, it starts by what's going on? Yeah, so first of all, it actually starts by doing this computation, which is an like integer value. It takes the center angle minus the width divided by 2 minus now the minimum, like the minimum angle over here, divided by the increment that we defined actually here. And then yeah, it sort of just does this, and then it ends by doing this computation, it starts with some sort of maximum like start and then ends here with n minus 1. Here it's just sort of like ignoring infinities, which is not required. And now here we're trying to get, I think like 4 or 5 laser scans. Okay, so the first one is like getting the front range. So basically the robot actually, as we can see here, it moves forward. So it only can actually go either to the front, to the left, or to the right, or to the front left, or to the front right. So those are the 5 movements, or 5 like optimal movements that it can actually make. And in that case, we try to get like the front range, the front left range, front right, and then left, and then right, whatever is specifically right, based on the robot movement. So after we've actually collected defined the methods to get also like laser data based on the 5 directions the robot can actually take, we now try to, okay, so it will run all tests that were actually sort of predefined. So it will stop the robot at first, and then it will move the robot towards the front for 0.2 seconds, and then it sleeps for like 0.5 seconds, and it stops the robot. And if it has to make the movement to turn left, so it checks all of these before making, like, if all the tests are actually now passed, and then now the obstacle avoidance is going to start, right? As we saw here, it did check everything first, and then when all the tests were actually passed, and then now it started the obstacle avoidance like loop. So basically when we come here, so first of all, okay, I did set like the forward speed to 0.2, and then the speed to 0.5, and the threshold to 0.4. So basically, as long as the threshold is greater, the front value that we actually get is greater than the threshold, the robot can actually keep moving forward, as we can see here. Else, if it's less than the threshold, and then it has to stop the robot and get these laser scans and now decide, okay, which is the best direction that it has to take, right?
Okay.
So it has to like go to the front left, front right, left or right. That's what's basically happening here. We see the robot coming. It has detected an obstacle. It stops, gets sensor values, and then based on that, it decides the best direction to follow, and then it follows that direction. And then now here, it just spins until like our front is clear, and then it does this loop over and over again without bumping in any obstacle, whether it's the wall or like any like traffic signs or obstacle like that brick that is in the smart city.
So the robot, the class version is doing the exact same thing. Is that right? All right. So
I will explain the class version. It's doing the same, the exact same thing, but like the code structure is not the same, because like here we are just defining, right? But like in the class, we are doing object-oriented programming. So there we have like a class and object, and now the object has its own methods in it, as compared to just defining several methods over here.
All right, let's see that. Let's see that. I think given the time we've got,
Okay. So now in the class version, it's actually the same structure, but just the code actually changes. The code structure changes. Here, instead of defining methods, we just define one class, one object, which is robot control. And then here in this object or in this class, we now define these methods. So these are things that I like already talked about in the no class version. So basically the things like stopping the robot, moving front, turning left, turning right, giving it some sort of like instruction to move a front for a certain time, and here also moving front for a certain distance, and so on and so forth. So it's still the same thing, but like this one is sort of like embedded inside the robot control class or object that we have here. So it makes it like much more, object-oriented programming as compared to the other one that doesn't use Python classes or Python objects. So basically, everything is defined in this, whether it's the methods and also even the loop, right? Like the laser scanner loop. And then after that, now we try to harness everything here. And then, also defining the obstacle avoidance in here. All of them are in the class. And then after we've done all of these in here, what actually happens, we just call the class here to do the work. That's all.
All right, all right. And what benefits
And
did
we
you
can.
find in implementing the class version versus the non-class
Mm,
version? Or if you found the procedural approach to be more beneficial, can you give
yeah.
detail to that?
Okay. I think both approaches are actually good, I would say. It all depends on the kind of project that you actually have. If it's a small scale project, if you go with procedure-oriented program, it's actually okay. Like where you have just a few lines of code and stuff like that. But like when you have a very big project, like you have to write like thousands of lines of code, it's always best to go with like OPP, with object-oriented program, OOP,
Mm-hmm.
actually. So this one is way more better as compared to that one in terms of structure, even though they both achieve the same goal, right?
Mm-hmm.
So I would say this one is a lot more efficient when you're working with a large project or with a large code file or large code base. And then the other one, if you have a very like slightly small project, you can actually go with that one, with the other one. Yeah.
All right, all right. Can you explain to me what is the purpose of the init function, right? Can you give more detail with regards to that in the class version?
Okay. What this one actually does here, the init function that we have here, it just sort of initializes the Python class or the Python object, right?
Mm-hmm.
And then like we know a Python object actually has like attributes and also like the function that we have in here. So like basically as we can see, this one is different. When we look at if I open this one, it will disappear. When we look at this, when we are defining methods, we don't need to call like self dot something
Mm-hmm.
before like the method. But like when we go into the class version of it,
Mm-hmm.
so here, first of all, we initialize here the robot control object by
Mm-hmm.
saying, okay, initialize it, and then self is going to be like the keyword that we actually call, and then dot, we call the parameter, like robot interface linear velocity, and all of these like robot interface are coming from this robot interface that we imported from this module.
Mm-hmm. So
Um,
okay, all right.
what
So
it does initialization.
all right,
Yeah.
initialization. So what is
Mhm.
happening in the process of initialization? Is it just assigning values to variables? What's going on in that process?
No, it's not assigning values to variable. Like basically here it's initializing and calling this robot interface module. And then in it's going to say, okay, we have imported this robot interface in here. And
Mm-hmm.
then anything that declaring here as self are going to be part of this, like this module, this robot interface module. So it just helps us write Python code that calls, other ROS robot interface code that allows us to interact with the robot without writing any ROS program. So
Mm-hmm.
what it does is just like initializing it and saying that okay, anything that we're doing here is being like sort of drawn uh from the robot interface like module,
All
as
right.
we can see here. Like every time we're doing this, we just call self and then dot, which means it's going to be of this type.
It's going to be of that app. All right. All right. All right. Are there any other
Yeah.
bits that you'd want to explain for the 2 minutes that we've got?
Um, Basically, I think we've gone through the questions you asked, and except for the simulation, uh, and also for the robot working the code working on the real robot, and explaining the code and answering the questions. I don't think there is any comment, except that I would maybe encourage people or like anyone trying to get into robotics, especially when you're working with Python scripts, just to when you have a very small project, it's okay to go with procedure-oriented programming.
Mm.
But when you have a very large version, the most efficient and like optimal one is using like object-oriented programming to help also the other people that are working with you on the same code.
Mm-hmm.
Yeah.
Modularity, right? So you want to ensure that you can be as modular as possible for the sake of
Yeah.
maintenance.
Yeah, absolutely. Yeah.
All right.
Yeah.
All right. All
Yeah.
right.
We'll just encourage people to go with that.
All right.
Um,
Thank you very much for your presentation, Francois. So we'll just head on and we'll
all right. So should I start the show now?
yes, fantastic.
Okay.
All right, everyone. This was Francois' presentation, and a warm congratulations to him. I'd like to encourage all those of you who would like to give a shot to this project to try it, and then you can come and showcase your work. So until then, we keep pushing your ROS learning.